Okay, let's continue. So towards the end of last class, we saw how to increase the gain of our amplifier. So we essentially took a step back. Yeah, we noticed that we started with a simple common source like this. Then to increase the gain of this fellow, we then we move to this so that we can take difference between two voltages. And then to increase the gain of this amplifier, we decided to replace the resistor with a current source. So that gave rise to this. And this is the differential picture. And finally, we did this biasing like this to mirror the current, right? And then we saw, instead of having a PMOS as a current source, we can make a better current source using a cascode of PMOS. But this did improve the output resistance looking up, but looking down it was still limited by R0 of this transistor. So the solution was to have a cascode on both the NMOS and the PMOS side. And then we constructed a differential version like this, and we also saw that this is the main current source. So if we want to bias it with a particular current, we should be fixing the gate voltage of this transistor, and this we could do a self biasing like this. It's the same thing earlier for the 5 transistor OTA. This was not there, this was short, so we were doing it. Now we have an extra current buffer in between. And yeah, as I mentioned, we could also do the biasing like this. We can do 2 diode connections like this. So in today's class, we'll start from this and see what is the difference between these two. So let me first copy this. So as I mentioned, this is called the telescopic cascode. Let me also have it. So let's quickly analyze this. So let's do the small signal calculation. Again, let's not do the calculation from scratch. We'll reuse the result that we know from the 5 transistor OTA calculation. So just to rewind it back, in the 5 transistor OTA, if I look at the short circuit GM, it is from GM of which transistor? M1 or M2. Rout is essentially output resistance of this in parallel with output resistance of this. That is the final expression. So with that in mind, can you tell me what will be the short circuit GM here? Which transistors will contribute to the short circuit GM here? M1, M2, because that is actually taking the voltages and converting it to a current. No surprise that this is roughly the short circuit GM. Similarly, what is my Rout? I mean, again, in the 5 transistor OTA case, wherever it was, the final expression was simple. It was the resistance in the upside, resistance here in parallel to the resistance here, that's all. Similarly, here it should be the resistance of this in parallel to the resistance of this. So what is the resistance of this structure? What is this? If you didn't have this at all, what would be the resistance here? R0 of 8. Now we have an additional fellow here. What is the resistance now? GM6, R0 6 times. Remember, this is basically your cascode. Similarly, looking down, not looking down, I would say the expression will have this impedance in parallel. What is the resistance of this alone? GM of GM4, R0 4 times, R0 2. Okay. So I'll just directly write it. Again, this doesn't mean that looking up the resistance is this, looking down the resistance is this. In fact, I'll give it as an exercise. Please calculate. The results will be similar to what you had in the 5 transistor OTA. Just that instead of having one R0, you will have a cascode impedance. That's all. So, which means your small signal gain is good. So, we'll not look into it further. Let's look at the DC biasing and large signal properties. So let me copy paste this. Okay, let me erase this. So I'm looking at the DC operating point. So firstly, tell me if I call the currents here as I1, I2. I'll mark here. So what do you think will be the values of I1 and I2? I0 by 2, I0 by 2. Again, remember the circuit is asymmetric, but once again you can make the same argument. We can assume that this drain voltage is not equal to this drain voltage, and if you try to argue, you will end up with a contradiction. So the consistent solution is I1 must be equal to I2, in turn must be equal to I0 by 2. So again, this circuit is asymmetric, but as long as you provide what kind of excitation? Common mode excitation, this becomes symmetric. Okay. Great. So then tell me, what is this voltage Vx? What will determine this voltage Vx? How will VB determine this voltage Vx? Yeah, remember that the current flowing through this transistor is fixed to be what value? I0 by 2. If the current through the transistor is fixed, what should get fixed here? So which means, what is Vx now? Can you tell me? It is the gate voltage VB minus the gate to source voltage of, let us say, M1 or M2 at a current of I0 by 2. Right? The same thing as we saw in the 5 transistor OTA, no change. So now let's look at these voltages. I'll call this VD1, VD2. Once again, you can show that these two voltages have to be equal. That is the only consistent solution. But what is determining this voltage here? Huh? How VB4 is fixing this voltage? What can you say about the current through the transistors? I0 by 2. So which means now you can think of it like this. I have this transistor. At the bottom I have a current source with a value I0 by 2. I am fixing the gate voltage. So which means the source voltage has to get fixed so that it carries the required current. Correct? It is, again, you can think of this as a constant current biasing being done for this transistor now. Okay. So what is this voltage now? It is determined by VB4. So what is the value? VB4 minus VGS of which transistor? M3 or M4, both are same here. So I'll write it as VGS4 at what current? Not bit. So similarly, let's do this. Let me call this VD3 and VD4. So once again, VD3 has to be equal to VD4. But how is this voltage getting set? Gate voltage of? Yeah, remember this drain is same as the gate voltage of M7. Once again, what is the current flowing here? So if the transistor is in saturation and the current is fixed, what should get fixed? VGS. For the PMOS it is VSG, right? So if I mark this as VSG, now help me write this voltage now, gate voltage. This is the supply VDD. So it is going to be the source voltage here, which is the supply VDD, minus the source to gate voltage of M7 or M8. So let me write it. This is VDD minus VSG of M8 at a current of. Is that clear? So similarly, let's do this VD7, VD8. So VD7 has to be equal to VD8, that much is clear. But what is determining these voltages here? How M6 is determining? Yeah, once again, what is the current flowing here? Right? And remember here among M5, M7, which is the actual current source, or M8, M6, what is the actual current source? M8. So now we can think of it like this. For the PMOS transistor, M8 is the current source and M6 is like this. So which means if I fix, if I push in this current here, we have negative feedback setting this voltage. So if I connect this to VB6, the source voltage also should get set to the required value. So what is now this voltage VD8? Can you tell me what is VD8 equal to? I mean, you just told what is determining this voltage VD8? VB6. So yeah, let me make it. This is VB6. And for the transistor, what is getting set? The source to gate voltage. So this is my source to gate voltage. Now you should be able to tell me what is VD8. VB6 plus, I'll say VSG of M8 at a current of. So gate voltage plus the source to gate drop, that gives this voltage. Oh yeah, so thank you. Yeah, see, I made an intentional mistake to check if everyone is paying attention. Yeah, it is VSG6. Thank you. Yeah. VB6 plus VSG6 at I0 by 2. Okay, so that's with the operating point. Now let's also calculate the input common mode range and the output range, because we know finally this will be used in some kind of negative feedback. We want to specify the limits, so let's do that. Keep it down. Oops. So here I'll assume that I have the ICM, the input common mode, because I know in negative feedback both the inverting and non-inverting terminals will be at the same potential. I am calling that VICM. So I'll replace this with a NMOS transistor. So this is biased at a current I0, transistor is M0. So let's try to find the range for VICM. So let's try to write it directly, right? So let us say VICM is reducing. If the gate voltage here keeps reducing, which transistor can go out of saturation? M1 or M0? I mean, for here, if I see the gate voltage of the NMOS transistor is reducing, is it good or bad? Why? Yeah, for NMOS, drain voltage has to be sufficiently larger. So if gate is dropping, this transistor will not have any issues. But what will start to get affected? Why? Yeah, remember the VGS of the transistor is fixed. If I keep reducing this voltage, Vx has to drop. And as Vx drops, you will not have sufficient VDS for M0. So let's try to write it directly now. Remember that my VICM, or this gate voltage, this is the VGS of this transistor, yeah, plus the VDS of this transistor. So VGS I know is fixed, right? So we can write it directly. This is going to be the VGS of the transistor M2 at a current I0 by 2, plus the VDS. What is the minimum value for the VDS? That is the overdrive voltage for which transistor? Biased at a current time. Again, this is limited by M0. I mean, if you recollect, this is same as your 5 transistor OTA. Nothing changed because this part of the circuit is same as before. Is it clear? You'll try to write it directly. If not, you can do the same. You can find out what voltage is limiting the transistor to be out of saturation, and then write it slowly. You find what is the minimum this voltage can have, and then in terms of this voltage you can write what is VIC. Same thing. Any confusion on how I wrote this? Okay, so let's move on. Let's look at the upper end. Now I'm increasing the gate voltage. Which transistor can go out of saturation now? Yeah, I'm increasing the gate voltage of the NMOS transistor, which means this can go out of saturation. what is the maximum the gate voltage can go compared to the drain? Yeah, remember the maximum gate can go one threshold above the drain, right? Similarly, the drain can fall one threshold below the gate. It's easy to remember. So the maximum gate can go one threshold voltage above the drain voltage, and I already know this drain voltage is this fellow. So I'll directly write it. This is my drain voltage. I am writing it here. So it is VB4 minus VGS4. So first I am writing the drain voltage, which is VB4 minus VGS4 at a current I0 by 2. This is my drain voltage, and my gate can go at the max one threshold above than that. Right? So this is again limited by M1 or M2. Is it okay? I am trying to write it directly, but if you have doubts, let me know. We can go through it in detail. No worries. Okay. The first step is to understand if you increase or decrease a particular voltage, which transistor can get affected. Once you recognize that, the rest is easy. Okay, so now let's look at the output range. Again, let's look at the lower end. So the drain voltage here is reducing. If this voltage reduces, which transistor can go out of saturation? M4 or? Yeah. Why? Because the drain voltage of the NMOS transistor is reducing. That can go out of saturation. So what is the minimum the drain voltage can drop to compared to the gate? The minimum drain can take is one threshold lower than the gate. Easy to remember. It is the gate voltage. What is the gate voltage of this transistor? VB. The gate voltage is VB4. So drain can go one threshold lower than that. So it is VTH of which transistor? Because you are limited by M4 or M3. Is that okay? So similarly, let's look at the upper end. Now if Vout is increasing, which transistor can go out of saturation? Yeah, remember this is the drain voltage for both M4 and M6. Now for a PMOS transistor, drain voltage cannot be higher than the gate, right? So if the drain voltage keeps increasing here, M6 will move out of saturation. Again, for a PMOS transistor, what is the maximum the drain can go to? It is again maximum it can goes one threshold above the gate, right? Similarly, minimum gate voltage can drop will be one threshold below the drain. That way it's easy to remember. So it can go at the max one threshold, which is mod VTH6 above the gate voltage. What is the gate voltage here? It is VB6. I am limited by M6. Is it okay? Again, remember here everything here is known to me, right? For example, I know what is the VB4 because I am going to apply some voltage VB4. Similarly, if I say what is the transistor number, I know what is the mu n C ox W by L of the transistor. I know the threshold voltage of the transistor, which means if I specify the current, I can find this voltage VGS, right? Nothing here is unknown, right? This is not something arbitrary. It is shorthand notation for long expressions. That's all. Great. So similarly, let's actually try to find the absolute minimum and maximum Vout can take. So the lowest Vout can go will be determined by what? I mean, Vout minimum here is VB4 minus VTH4. If I want to find the absolute minimum for Vout, I should be looking at the absolute minimum for, correct? So let's do that. Where is this? So let me try to find VB4 minimum. Again, the exercise is similar. I will now try to reduce my bias voltage VB4. I will find which transistor can move out of saturation. Right? So tell me, I am reducing this gate voltage. which transistor can go out of saturation? M? Yeah, why? Yeah, once again, remember the current in the branches is fixed to I0 by 2, which means VGS is all fixed. If I reduce this gate voltage, since the VGS is fixed, the source voltage of M4, which is also the drain voltage of M2, will start to drop, which means these fellows will move out of saturation. Yeah? So we can try to write it directly. So help me. VB4 is this VGS plus VDS of M2 plus VDS of M0. So now let's write it. My VB4 is VGS of M4 at a current I0 by 2, correct, plus I am looking at VDS of M2. I am looking at minimum VB4, so I should look at minimum VDS. And how much is that? Overdrive of M2 at a current I0 by 2. Clear? So the third component is VDS of M0. The minimum of that VDS is also overdrive. So overdrive of 0 at a current I0. Okay. So now we know the minimum of this voltage. Let's try to find the minimum of Vout. So minimum of Vout is this voltage minus a threshold. So I'll write it directly. I have minus VTH4. What does it simplify to? Here I have VGS4 minus VTH4. What does it become? Right. So I can write it directly. Let me do that. So this is going to be overdrive of M4 at a current I0 by 2 plus overdrive of M2 at a current I0 by 2 plus overdrive of M0 at a current I0. Again, you can look at the circuit and also try to guess this. Ideally, I want my Vout to reach as close to 0 as possible. But no, I cannot do, because I need to have one VDS across M4, one VDS across M2, and one VDS across M0. So the minimum I can go is minimum VDS for all the three. That is basically the 3 overdrive voltages. But once again, I want to remind you that Vout reaching this minimum value is conditional upon the fact that I use the minimum voltage for VB4. Okay. If VB4 is connected to some other voltage, Vout can go that VB4 minus VTH. Since you have independent control on the gate voltage here, it is assumed that you are using this minimum VB4 so that the output can reach that minimum value. Okay. So this is the minimum. Similarly, let's look at Vout maximum. Vout maximum is VB6 plus mod VTH6. So to find the absolute maximum of Vout, what should I look at? Let's look at maximum of VB6. So exercise is same. I'll now try to find, if I increase VB6, which transistor can go out of saturation. So I am increasing this voltage. What will happen? M3. Why M3? M3 is here, VB6 is here. Yeah, remember that if I increase the gate voltage here, once again the source to gate voltage of this fellow is fixed. So which means if I increase VB6, this voltage has to increase. So for a PMOS transistor, the drain voltage is increasing, which means these guys can go out of saturation. Is that clear? So again, let's try to write it directly. This is my voltage VB6. This is basically VDD minus the source to drain across M8 minus source to gate across M6. Fine. So tell me, so VDD is basically source to drain minus source to gate, of which source to gate voltage is fixed. So if this has to reach maximum, this has to be the minimum. So can you tell me directly what will VB6 max be? It is going to be VDD minus, I should drop minimum possible voltage across this. And what is the minimum possible voltage across this? The overdrive voltage of which transistor? at a current I 0 by 2 minus this voltage which is fixed, we don't have a control, or I would say we can't arbitrarily reduce it. So this is VSG of which transistor? M6 at a current I 0 by 2. Cool. So now let's write the maximum here. Vout max is this VB6 plus a threshold voltage. So this is going to be plus mod VTH6, right? So that will be VDD minus overdrive of M8, and what will this be? So I can now write it directly. This is VDD minus overdrive of M8 at a current I 0 by 2 minus overdrive of M6 at a current I 0 by 2. So again, you can also guess this by looking at the circuit. Ideally, I want my Vout to reach VDD, but of course now I can't do it because I have to maintain two source to drain voltages, and those are basically the two overdrive voltages. But once again, the point to have in mind is, when can Vout reach this maximum value? If I use a maximum value for VB6, correct? If VB6 is not this value and something else, then it will be that something else voltage plus mod VTH6. The point to notice, I have free control on the gate voltage here. That's why we are able to make this claim. Is it clear? Okay. So now let me show this variant. In the last class, we also saw we can also generate the bias voltage this way. That is, instead of doing this direct connection, I can also do this. So let's look at the second candidate also and see what is good or what is bad. So I'll say this is VICM. So here I'll not do all the calculations. I'll give it as an exercise for you to work out the short circuit GM and R out. In fact, the result will be same as what you computed for the other variant. Similarly, you find the operating point. Okay, these are exercise, you please work out. But what I want to focus on is the maximum the output can go here. Let's look at that alone. So again, the idea is same. If I keep increasing Vout, which transistor can go out of saturation here? The drain voltage of PMOS transistor is increasing, that can go out of saturation. So what is the maximum the drain can go now with respect to the gate voltage? Yeah, if I call this, let us say VG6, VG6 plus mod VTH6. So let's find out what is the VG6, right? So first of all, tell me what is this voltage? So what is determining this voltage? Yeah, current. I mean, this is also the gate voltage of M7, M8, right? What can you say about the currents in the two branches? Again, you can argue they will be same, I 0 by 2, I 0 by 2. If the currents in the two branches are fixed, what should get fixed now? So what should be this voltage now? If this is VDD, VDD minus VSG of, let us say, I'll call it M7 or M8, the current I 0 by 2. So you know this voltage now. Can you make a comment about this voltage? So if I look at this voltage, what will that be? Remember, this is the source voltage. I know the source voltage, which is this value. This will be one source to gate voltage smaller than that. So the source voltage is VDD minus VSG8 at a current I 0 by 2. So this will be minus VSG6 at a current I 0. Okay. So now we know VG6, let's put it here. So this is going to be the gate voltage, which is VGD minus VSG8 at a current I0 by 2 minus VSG6 at a current I0 by 2 plus mod VTH6. Right? So how does this simplify? I have minus VSG plus mod VTH. That will become the overdrive voltage. So this is VSG8 at a current I0 by 2 minus overdrive voltage of M6 at a current I0 by 2. Okay. And now I can massage this equation slightly. So let us say I add mod VTH8 and subtract mod VTH8. Same. So how will this simplify as? So basically I can rewrite it like this. It is VDD minus overdrive of M8 at a current I0 by 2 minus overdrive of M6 at a current I0 by 2 and else, and then what? Minus mod VTH8. So now if you compare this with the other variant, the maximum output could have gone as VDD minus the two overdrive voltages, whereas here it is the two overdrive voltages and one threshold lower. So again, that's why I am saying you can't just look at the circuit and say this is VDD minus overdrive voltage minus overdrive voltage. That is not correct. There you could say, because the gate voltage was freely accessible to you, you can connect this to the required maximum voltage, whereas here the gate voltage is defined to some other value. So which means the maximum the output can go will be just one threshold above the gate. Yeah. This one. Yeah. This voltage is okay. I mean this is same as the source voltage for M5, and this is basically source to gate of M6. Okay. So this voltage is basically the source voltage minus source to gate of M6. So that's why you can't randomly say that, hey, this max I can goes VDD minus 2 overdrive voltage. That is not correct. That can happen if you have independent control on the gate voltage, because fundamental limit is basically the fundamental battle is between gate and drain. Right? Max drain can go here is one threshold above the gate. That's it. So which means, again, as I say, anytime you come up with something new or find something new, you should look for a name or give it a name. And this is the first variant. The second variant is this. Now which of the two is better, left one or right one, with respect to the gain? I mean with respect to the swing. Left one is better. So for obvious reason, this is called the high swing cascode, or I should be clear. Let me. Oh, sorry. Yes, again testing your. No. So now left side is better. So this part in particular, because this is the only thing that is different, right? So this is called the high swing cascode, because the output swings is higher. Because this is also a PMOS cascode, this is also a PMOS cascode. The only difference is in biasing, generating the bias voltages here. Correct? Here you didn't have to generate any additional voltage, you could directly get this. But of course the price you pay is that the output maximum is limited. Whereas if you do some extra effort and generate this required voltage and connect it, the output can reach much higher voltage. Same thing in life, take extra effort and work hard, your max you can go higher. Great.